This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to today's discussion. We're diving into an interactive physics simulation designed to teach dynamics and forces, specifically focusing on the interaction between two blocks. It's a fascinating example of how technology is enhancing education.
Indeed. Interactive simulations offer a powerful way to engage students and provide a hands-on learning experience that goes beyond traditional textbook learning.
The simulation uses a compressible spring between the blocks. How does that element enhance the learning experience?
The spring allows students to directly manipulate the contact force between the blocks, observing the effects on their motion in real time. It's a visual and intuitive way to grasp concepts like compression and expansion.
And it's all built using HTML5 and JavaScript, making it accessible across various devices. Let's explore the details. Let's start with the overview. The simulation aims to teach dynamics and forces, primarily contact forces. It's an open educational resource, freely accessible and adaptable.
Precisely. The open-source nature is crucial. It allows educators to modify and integrate the simulation into their existing curriculum, tailoring it to their specific needs and student levels. The HTML5 implementation ensures broad accessibility, eliminating the need for specialized software or plugins.
The simulation boasts several interactive features. We have combo boxes and sliders to adjust parameters, a compressible spring for manipulating contact force, and even dragable texts for interface customization.
The combo boxes and sliders allow for controlled experimentation. Students can systematically change variables and observe the resulting changes in the system's behavior. The dragable texts are a nice touch, allowing for personalized learning experiences. The full screen option enhances immersion.
The target audience is both teachers and students. Teachers can use it as a teaching tool, and students can use it for self-directed learning. Technically, it's built using JavaScript and HTML5, and it's easily embeddable in web pages using an iframe.
The simulation's design caters to diverse learning styles. Visual learners benefit from the dynamic representation of forces and motion, while kinesthetic learners engage through the interactive manipulation of the simulation's elements. The ease of embedding is a significant advantage for educators.
The simulation was developed by Fu Kun Huang, Fremont Tang, and Lu Kang Wei. The website also lists many other related simulations covering a wide range of physics topics.
The availability of numerous related simulations creates a rich learning ecosystem. Students can explore various concepts and build upon their understanding through a diverse range of interactive experiences. This interconnectedness is a key strength of the open-source Physics at Singapore platform.
The content is licensed under the Creative Commons Attribution Share Alike 4.0 Singapore license. The document mentions sample learning goals, but they aren't explicitly stated.
The Creative Commons license promotes widespread adoption and adaptation of the simulation. The lack of explicitly stated learning goals provides flexibility for educators to define their own objectives based on their students' needs and the specific context of their lessons.
The accompanying study guide includes review questions, a quiz answer key, and essay questions to deepen understanding. The FAQ section addresses common user queries.
The study guide provides a structured approach to learning, reinforcing the concepts presented in the simulation. The FAQ section proactively addresses potential user challenges, enhancing the overall user experience and promoting independent learning.
How well does the simulation illustrate Newton's laws of motion?
The simulation effectively demonstrates Newton's first law, inertia, second law, FAPMM, and third law, axial reaction, through the interaction of the two blocks and the spring. Students can observe how changes in force affect acceleration and how the forces between the blocks are equal and opposite. The compressible spring visually represents the contact force, showing how it changes with compression and expansion.
How does this simulation compare to others on the Open Source Physics at Singapore website?
While each simulation focuses on a specific concept, they share a common design philosophy: interactive learning through manipulation and observation. The pushing on two blocks simulation excels in its clear focus on contact forces and the intuitive use of the compressible spring. Other simulations might offer more complex scenarios or different pedagogical approaches.
What are the benefits and allocations of using simulations like this in the classroom?
Simulations offer a safe space for experimentation, allowing students to explore concepts without the constraints of real-world limitations. They can manipulate variables, observe immediate results, and repeat experiments easily. However, simulations can't fully replicate the complexities of the real world, and they might not foster the same level of critical thinking as hands-on laboratory work. A balanced approach, integrating simulations with traditional methods, is ideal.
How could a teacher integrate this simulation into a lesson plan?
A teacher could introduce the concept of forces in motion, then have students use the simulation to explore the relationship between force, mass, and acceleration. They could design experiments to test Newton's laws, using the sliders and combo boxes to manipulate variables. Post-simulation discussions could focus on analyzing results and connecting the simulation to real-world examples.
The simulation's strengths lie in its interactive nature, accessibility, and clear focus on fundamental physics concepts. What are some areas for potential improvement or expansion?
Adding more sophisticated features, such as friction adjustments or the inclusion of different types of surfaces, could enhance the simulation's complexity and realism. Incorporating assessment tools directly into the simulation would also be beneficial. Further development could explore the integration of data logging and analysis capabilities.
This simulation is a valuable tool for teaching dynamics and forces. Its open-source nature and interactive features make it a powerful addition to any physics curriculum. Thank you for this discussion.